Today we are going to talk about some of the important concepts to understand before you begin studying strengths of materials here at BYU-Idaho. In the beginning of the class, you should understand the following: internal reactions, forces and moments, sign convention for internal reactions, stress, and factors of safety. We will go into more detail about each of these bullet points throughout this video. Internal reactions is the basis of strengths of materials. Before you can learn about stresses, you need to be able to find the internal reactions, because the stress is determined by the internal reaction and the area that is spread out across. What we are referring to when we say an internal reaction is what the material must feel at a specific point in order to properly withstand the force that is acting on the material. This means that the internal reaction will vary depending on the loads that are applied to the material. This could be at point loads, distributed loads, pressures, or bending. Whenever you have a change in loading, you will have a different internal reaction. This means that if you have a distributed load, which changes loading at every point along the member, you will have a different internal reaction at every point. When we want to find the internal reaction at a specific point, you should make a cut at that point you are interested in. That way, you can find what the internal reaction must be in order for that cut piece to be in static equilibrium. We won't worry about dynamic or accelerating forces in this class. Everything will be static. This idea of making cuts is similar to the ideas that you will have to do in statics when you are finding forces and trusses. You can use this as a basis, but there are some differences, mostly because we will be treating the material as a fixed wall support, meaning that it can have axial reactions, vertical reactions, and moment reactions all at once. Hopefully this will make more sense as you practice them. Now let's try and illustrate this idea and concept with a bit better. This is a beam. When you look at this beam right now, you'll notice that it is in static equilibrium, and that it is basically saying that their net force and moments that are acting on this beam is equal to 0. That being the case, I won't bother at this point adding any external forces. The point I want to make is that when you make a cut in your member like this, you'll be left with 3 reactions. First, you will be left with the axial reaction, which we will call the normal forces, and then a vertical force that we call the shear force, and the moment reaction. It should be noticed that these are the same reactions that you will see in a fixed wall support. We can also mirror these reactions and see them opposites on the other side. If you were to put these two pieces back together, they would cancel each other out. Now all we would have to do is look at either of the halves and sum forces in each respective direction in order to find the reactions. They should be static, or in other words, equal to 0. As you noticed, you have 2 different ways you can look at the members, but in this case, what would be positive and what would be negative? In strengths, a sign convention was developed in order to help organize what is positive and what is negative. First, to determine what is positive, we will look at the cut on the right and cut on the left. As you can tell, they should cancel each other out once they were put together. This is a positive sign convention, meaning that if it was cut on the right, this is how we would describe a positive shear, a positive normal, and a positive internal moment. Now this is what a negative example would look like. It's clear that it's the opposite, which makes sense because that's what negative means, opposite. So one important thing to point out that I noticed several students being confused on is this positive sign convention for shear. How is it that it's going down when the cut is on the right side? Most students can't seem to grasp that this is the sign convention for positive shear because usually negative forces go down. Just keep in mind that the shear will go down for positive shear when the cut is on the right side, but the shear will go up when the shear is positive on the left side. Here we will do an example problem of finding the internal reaction forces. Here we have a beam that has the following loadings on it. Since normal force loading doesn't change throughout the entire bar, it will be constant. However, the shear loading changes 3 times, from one end to the other. Those changes mean that we would have different shear forces here, here, and here. For this example problem, we will look at the internal forces at this point, which is 7.5 inches from the end. To help demonstrate that you can take your cut from either side and get the same answer, I will make the cut and look at both sides to solve them side by side. Solving first for the left side, since it is easier, and probably the side you would want to do, all we need to do is sum forces in the x and y directions and take a moment at the cut. Doing such will give us the following answers. 37 pounds for our shear force, which makes sense since it needs to counter-react the 37 pounds acting on it. 150 pounds for the normal force, which would counter-react the 150. And 27.5 inch-pounds that is acting due to the 37 times 7.5 distance. Looking at the other side, we would do the exact same process, summing forces in the x and y directions and taking a moment at the cut. But everything is more complicated since there are more forces acting on the beam. But in the end, we will get the same values. This is the value we would get if we were to take our moment at the cut by taking all the sum of each force multiplied by the respective distances, and we would get the same numbers for our normal, shear, and moment. Now that we have a basic understanding about internal forces, it becomes rather easy to find the stress in members. First, stress is defined as the force distributed across an area. They require the previously discussed internal reactions. For now, we're going to be talking about average stresses. You will learn more about complicated stresses with time. We will also only discuss shear and normal stresses for now, since they are simple to understand. With time, we will incorporate the internal moment, but as for now, we will only focus on these two internal reaction forces. We will also discuss a design factor or factor of safety. Now let's compare the two types of stress. First, normal stress. Normal stress is usually the most commonly understood stress, because we usually understand it as tension or compression stresses. When you take a bar and stretch it or compress it, it feels normal stress. When we want to think about what the stress distribution looks like, we can look at this example here. The force that was applied across that bar will be spread out across the cross-sectional area. Shear stress is something that's less understood usually. This is when you have two plates sliding against each other. I like to think of it like this. And this is what the shear distribution looks like. In both cases, they will use the same cross-sectional area, just they act in different directions. That means they don't combine, but they are stresses nonetheless. Factor safety is the easy part of this video. Materials will fail at specific stress values. We want to plan for our materials to always be less than that failure point. So we either decide an allowable stress or a factor of safety. Our factors of safety should always be greater than 1. If they are less than 1 at all, they will fail. So this is the equation for the factor of safety, where the factor of safety is equal to the stress that the material will fail at over the allowable stress that you wish to achieve.